So today I thought it would be very interesting to talk with you about some kinetics that I've been involved with, and I'm actually going to go all the way back to some of my graduate work at the University of Michigan and talk about some initial rates that I did in nickel-catalyzed reductive couplings, and I'm going to compare and contrast that to subsequent chemistry I did at the Scripps Research Institute using reaction progress kinetic analysis. So both of these projects involve inline measurements using ReactIR of full reaction progressions. These are both sets of real data shown here on the title slide, but the kinetic methodology to do one versus the other is very different. And so I'll sort of give you a flavor for each one, and you can tell that I'm sort of biased in one of these, but you can decide for yourself which one you'd like to do. So in a general sense, I'm going to sort of more or less split the talk evenly into two different topics, one being the nickel chemistry, and I'm going to use my method of initial rates where I have my reaction progression here. I'm going to look at the first 10 to 15, maybe even 20% conversion, call that my initial rate, and then use that to develop a kinetic model for this reaction. And this reaction involves the reductive coupling of an aldehyde and an alkyne. We call that an inal for the alkyne aldehyde, in the presence of a nickel catalyst and then a reducing agent. In this case, it's going to be a silane reducing agent, a silyl hydride, silyl deuteride, that kind of thing. And through the course of my work, I was able to get a full kinetic profile of this reaction, the order in the substrate, the reducing agent, the nickel catalyst. But just to get that information, using the method of initial rates, took 30 experiments. And that's 30 experiments that just go into the data to get that information, not any sort of troubleshooting or just generating, how I'm going to study this reaction in situ. And so you can already see where my biases lie, right? Compare that to reaction progress kinetic analysis. The second half of my talk, I'll talk about using graphical overlay and now the entire reaction progression, time zero to time final, to get as much kinetic information as you possibly can out of the entire reaction, one reaction at a time. And what we're going to do is just set these plots on top of each other and look at their relative rates based on the extent to which they overlay. And so you can see these two right here, because they overlay on top of each other very nicely, you can say those two reactions are going at the same rate. And you can use that sort of qualitative analysis to learn a whole lot about your reaction. And in fact, I'll tell you about how we got the orders in all of the stoichiometric species, the catalyst. We even learned about the level of catalyst stability in the reaction, product inhibition, and relative binding constants for off-cycle intermediates that affected the global rate of your chemical reaction. And we got all this information in as few as 12 experiments. So I will admit to self-plagiarization here. This is a slide from my thesis defense. I dug this out of my computer this week, and so I was in John Montgomery's group at Michigan, and so I say up to 2010, this was the state-of-the-art of nickel-catalyzed reductive couplings, because that's when I gave my thesis defense. But this just shows you that using a nickel zero catalyst and two different pi systems, typically a polar pi system like an aldehyde or a ketone, coupled with a nonpolar pi system like an alkyne or an alkene, you can access all of these different molecular frameworks. And so I can make my slides available later if you guys want, so you can see all these references. You don't have to worry about that now. But we're going to focus for the kinetics on this species right here. This is a silyl-protected allylic alcohol. And that comes from an aldehyde and an alkyne, and a silyl hydride as a reducing agent. And the reason we were so interested in studying this reaction and this molecule in particular is because of some unknown mechanistic features of this reaction. And so what I show here is a typical reaction of an aldehyde and an alkyne intramolecular coupling with a silyl deuteride and a silyl hydride. This is a crossover experiment. This is one of my favorite mechanistic experiments. It's a competition experiment, and basically, you can see I've color-coded it for you. Red goes with red, blue goes with blue. Is there scrambling of the silyl hydride and the deuteride into your products? And two different classes of ligands worked for this nickel catalysis, N-heterocyclic carbenes and trialkyl phosphines. And so with a mesotyl, so N substituted with mesotyls for the N-heterocyclic carbene, they gave products exclusively with no crossover. You can see the color coding matches. The ethyl that started with the deuteride ended up with the deuterium in the product. Propyl stays with hydride. So you have to develop a mechanism that fits with those two things staying together. Compare that to the trialkyl phosphine, you get extensive crossover, a lot of scrambling of the H and the D. So if you just looked at the ethyl product, you get a near statistical mixture, not quite, but extensive scrambling of H and D there, same with the propyl. So we have to be able to account for this difference in mechanism between the N-heterocyclic carbene and the phosphines. And this is really where our interest in studying this reaction lay. What is the silane doing? How does it participate in the reaction? And you can sort of, just pen and paper, go down and say, well, you can think of two sort of extreme limiting scenarios for when the silane participates in the reaction. First, maybe it participates late in the reaction after you've already done your carbon-carbon bond forming step, and then you just reduce that oxymetallic cycle with the silyl hydride. Compare that to direct addition into the silyl hydride bond with the nickel catalyst as one of the first steps, if not the first step. This now could lead to crossover via disproportionation or a series of hydrosylation events on the aldehyde and the alkyne that go with the carbon-carbon bond forming step that scramble the relative positions of the ethyl and the propyl. And so because there was such a difference in timing from where the silane sort of showed itself in this reaction mechanism, just based on our hypothesis, we thought, well, kinetics would be a really good way to say, does this participate late in the reaction or early? So we're going to do our initial rates, and we're going to see, is it one of the first steps? Does it have a rate dependence? Or is it one of the later steps, such that we wouldn't expect to see a rate dependence? That may be an oversimplification, but that's sort of, you know, as a young graduate student, how I thought about it. And so I changed up my reaction just ever so slightly. I'm going to use a tricyclohexyl phosphine ligand now instead of a tributyl, because the tricyclohexyl, in terms of relative rates, behave very similar to the N-heterocyclic carbene. They're both very fast. And in fact, you can see this was sort of an embarrassing discovery for our group. We typically ran these reactions at 0 degrees, or not 0 degrees, or room temperature, or 45 degrees overnight, right? The dubious overnight. When I put this on the IR for the first time and ran it at room temperature, it was over in several seconds. So I had to go down to -25 to get reasonable progressions to watch this reaction, and so that led to some sort of embarrassing discussions between my colleagues and our PI about why we're just leaving at 5 o'clock with the reaction stirring. But you know, maybe they don't like me too much for showing this, but I had to lower it to -25, and so we didn't get so fancy as to have an easy max quite yet, so we had to use this cryostasis bath, and I just used it outside of the hood. And I wanted to point out, so this is the instrument that we bought from Will. During this time, there was an NIH surplus, and our program officer contacted us and said, hey, do you need any new instrumentation? If you write us a memo, we will give you money for a new instrument. And so I, as a second-year graduate student, wrote a 2-page memo and got R45M React IR with the channel switching and 2 different probes, just based off a phone call from a program officer. It doesn't quite work that way now, but we were really well set up to do this chemistry. And so in a very simple way, you can just take your INAL, put it in whatever solvent you are going to run the reaction in, look at the very, very strong aldehyde peak, and I'm just going to say, I'm going to watch that aldehyde peak disappear because I know it goes from sp2 to sp3. You cleave that aldehyde into the protected alcohol. So I'm just going to watch the disappearance of that and call that my rate. A lot of people, when they think about doing IR or when they look at people doing IR, they're really, really worried about calibrating the IR to an ex situ method like GC or NMR, and I would argue that you don't really need to do that. You can take your absorbance data. This is a real plot off of, this is the old version of the software because this is old data, but if you just do a serial dilution, start at a high concentration and do a dilution and see how this peak changes at different concentrations, you can get a very nice linear plot here that relates your absorbance to the molar concentration, and as long as you're in a linear portion with respect to Beer's law, you're fine. You can read it directly off the absorbance. So you can take what you see off your IR trends, copy paste into Excel, and you have your rate data. But we always do the GC and the NMR anyway because it helps people sleep at night. We're going to do exactly what everyone learned how to do initial rate kinetics when they first learned it in organic chemistry or a higher level physical organic chemistry class. We're going to keep a lot of the things the same and change one of the things and see how the initial rate changes when we change the concentration of these species. So starting with the nickel catalyst, I'm still going to keep my 2-to-1 ratio of phosphine to nickel, and the initial rate that I'm getting from these different reactions progresses very linearly with respect to catalyst concentration. So there's a positive order dependence on my nickel catalyst. That's probably not super surprising that it's a positive driver for this reaction. And just to show there's nothing funny going on with this chemistry, you can look at the entire rate progression, the entire reaction progression, and see that these reactions all behave similarly. There's none of them that sort of shut down early or one that does something sort of wonky here in the middle. They have these nice, what appear to be first order or at least positive order decays. So we have a positive order on a nickel catalyst. You just repeat everything. You say, I'm going to do the same types of reactions, but now I'm going to vary my concentration of my inal starting material, also a linear progression of my initial rate with respect to concentration. So I did something here. This is kind of interesting. This plot here, if you're real sharp and paying attention, it looks like at 1.25 equivalents, where I started my highest concentration of inal. It looks like I started at about a negative 11 or negative 1,000 seconds, right? I didn't really do that. I started these all at quote 0, but I took my plot for the highest concentration of inal and shifted it over to the left so that when that reaction went down to 0.05 molar in inal, I could compare that to a reaction that started at 0.5 molar inal. That's actually a really important tenet of reaction progress kinetic analysis, and I didn't know what I was doing as a graduate student. I just thought the picture looked pretty, right? But this is a really important thing that you can extract a lot of information out of, and I said, oh, all I care about is this. I got a straight line, positive order in the inal. All right, so we have positive order in the nickel, positive order in my substrate. And so now the $64,000 question is, what is happening with the silane? What is the kinetic dependence on varying the silane concentration? How does that affect the reaction? And so you get what is effectively the least interesting kinetic plot you can get from doing this type of analysis, a flat line. 0 order rate dependence across a 4-fold excess of silane in this reaction. And if you don't believe me here, you sure as heck should believe me here. These are 4 different sets of data plotted on the same axis. You'd have to get pretty close to see that there's 4 different colors here, and that one of these represents a 4-fold excess of the silane. You can run this up to 50 equivalents of silane, and it's not going to change your rate. It doesn't move at all. So this fits with the metallocycle mechanism, a late incorporation of the silane into the metallocycle after some sort of rate determining step. But you can take it a step further and look at kinetic isotope effects, because people are interested, okay, well, if there is a possibility for direct insertion into the silyl hydride or silyl deuteride, you could be able to see a kinetic isotope effect. In a competition kinetic isotope effect using excess of each reducing agent, in the NMR, you measure as close as you can get to 50-50 mixture. There's no KIE. And I took this one step further. You can monitor the silyl hydride peak in your IR. So if you use a silicon composite probe, you can see at 2100 reciprocal centimeters, the silyl hydride stretch, have this reacting at the reaction temperature, and then add stoichiometric amounts of your nickel phosphine complex, and it doesn't do a dang thing. Nothing. There's no way this nickel is inserting into the silyl hydride as the first step of this reaction. It needs the other pi components in there to do anything at all. So this fits really well with our proposed mechanism, one of the proposed mechanisms, first order rate dependence in substrate, first order rate dependence in catalyst. You could argue a rate determining oxidative cyclization, and then a series of steps that involve the silane that are sort of kinetically silent. You can't see them using the kinetics. But that never helped us answer the question that we started out with: how do we get crossover when we change ligand classes to the phosphine? This reaction with the trialkylphosphine gives us crossover, but we're not seeing any kinetic influence on the level of crossover we're observing. And so to make a long story short and sort of cut to the chase, what we ended up proposing is 2 joined catalytic cycles where the second catalytic cycle basically comes online after the rate determining step. And so if you just focused on the left-hand side here, this catalytic cycle fits perfectly with our observed rate data. A rate determining step or series of steps from the nickel and the substrate to do an oxidative cyclization, that fits perfectly with my first order in nickel, first order in inal, and then a rapid series of steps with the silane. If this species can dimerize before it interacts with any of the silanes, now you see a potential for crossover, because if you keep your color coding, you can see the external nickel oxygen bond here splits the alkyl group from a silane and its hydride onto 2 different molecules. And then if a second silane comes in of a different identity and splits the other nickel oxygen, now the hydride ends on one molecule and the propyl ends up on the other. These are the products, just after reductive elimination, these are the products you get. Those are the crossover products. And you may be sitting there thinking, well, that's sort of a fantastical mechanism you're proposing. That doesn't seem very likely. But this actually fits perfectly with some of the results you could see in kinetic isotope effect experiments. If you guys have looking at rates versus competition kinetic isotope effects, there's always some ambiguity at whether you're looking at a product determining step or a rate determining step. And so this, you can view this as, here's the rate determining step, and we have a product determining series of steps after the rate determining step that still have a selectivity value, but are completely silent in terms of different kinetics. And so that fits perfectly with any sort of KIE experiment you'd look at. There's a really good Hartwig paper out that you can read about that. But we had other experiments to support this to go with the crossover, but it really took us a long time to get the kinetic data to even enter the realm of doing the other experiments that we needed. So to summarize this, what ended up being half of a PhD thesis, it took us 30 experiments just to get the data that we needed to decide we still didn't know what the silane was doing and had to do more work. That's not a failure or an indictment of the kinetics. The kinetics are what they are. But if we could have gotten there faster, we probably could have done a lot more in a shorter period of time if we had a little better way to do the kinetics. One of the problems with initial rate kinetics, one of the just inherent problems you have, is the way that you do them. If you have a generic reaction, A plus B goes to C, typically use a large excess of one of the species, so you have effectively saturated in that species. So its rate doesn't affect the reaction. And you check your initial rates here, and you only get 10% of your data, because you don't want to get into a realm where both A and B are changing at the same time. Two changing variables in one reaction, you don't have enough equations to solve that math, right? So when you're building up your chart here to get your kinetic information, this one piece of information from the initial rate gives me that dot there, right? And what happens with the rest of the data, 90% of it, I throw it away. I never looked at it. All these graphs I'm showing you, this all data, this is real data. I have this data somewhere. I didn't do a damn thing with it, nothing. But if you're clever, you can see that one of the concentrations you need to fill out one of the data points on your rate versus concentration plot is embedded within the one reaction you already ran. It's there already. And if you thought about the entire reaction progression, you have rate data from time 0 to time final throughout the entire thing. Anytime you're changing concentration, you have rate data. And so reaction progress kinetic analysis takes advantage of this fact with one little trick. So I was going to say, oh, there's no trick to doing RPKA. There's one trick. The value of excess is the trick. So A and B, if they really go A plus B goes to C, those two values of A and B, their molar concentration, are linked to each other by their initial concentrations. The stoichiometry that you start with gives you this value of excess. You have a B in excess of 0.05 molar compared to A. And if you just simplistically went through 0%, 25%, 50, 75% reaction conversion and calculated what your A and your B should be, that value of excess should not change. It should be constant throughout the entire reaction, assuming A plus B goes to C, not C plus D plus EFG. But what you can do now is you can write A in terms of B or B in terms of A and reduce the number of variables that you need to solve for when generating kinetic rate law. And that's fine, that's great, right? So you're with me so far. This was perfectly outlined by my postdoctoral mentor at Scripps, Donna Blackman, and she has a flow chart here in a paper that's about 12 years old now that shows you how to do RPKA. The problem with this is the graphs that you generate from here to solve what she calls graphical rate equations look like something most people are not familiar with. You have a graph here that plots rate with respect to inverse concentration of one species with respect to concentration of other species. What does that mean? How many times do you see a plot like that? There's this barrier to doing RPKA that a lot of people say, nah, I know what an initial rate looks like. I'm just going to do that, right? So during my time at Scripps, we worked very hard on developing a much more user-friendly way to do reaction progress kinetic analysis that doesn't involve generating graphs with these sort of wonky X and Y axes. We just want regular data, regular reaction progression data, and we're going to do qualitative analysis using the overlay to learn about the kinetics. And we're going to showcase that in a CH activation reaction that was designed by Jin-Kwan Yu's group, also at Scripps, and it's an olefination reaction. So it's a directed CH olefination to give you this conjugated product. You don't need to really worry about what the reaction mechanism is as shown here. This was their hypothesis. And as a first hypothesis, these are the series of fundamental steps you would have to go through to get from A plus B goes to C. They were really interested in nailing down the kinetics of this reaction and for us to answer the question, why do these protected amino acid ligands have such a dramatic effect on the rate of the reaction? That's probably not so surprising. Running something ligandless is not the best way to run a reaction, but they wanted to know sort of, structurally or kinetically, how do they play a role in this reaction? And so we're going to do the same thing. I'm going to get my waterfall plots on my IR. I got my absorbance values, and I will admit we did do ex situ correlation to the in situ data, but I would still argue you don't have to do that. It's not necessary. And I've never once done this where it hasn't matched. Never once. But you can do that. The reviewers like to see it. It helps them sleep at night. So the reaction is doing what we say it's doing, right? And so I'm going to show you how to use RPKA from the data that you get. That's very simple, just consumption of your starting materials in your reaction. And there are two protocols you need to know about doing RPKA, a same excess protocol and a different excess protocol. And that's everything you need to know about running this kinetic method. The same excess protocol is just what it sounds like. You're running two different reactions, A and B, with two different concentrations of your species. I'm calling this 1 and 2. But the difference between them is going to be the same in each of those reactions. That's my same excess. And we're doing that on purpose because there's a point in reaction A at which it should have the same stoichiometry in species 1 and 2 as the starting stoichiometry for reaction B. If 1 plus 2 goes to product, and there's nothing funny going on in there, this value of excess ties these reactions together, and you can just read the concentration value of 1 right off the plot. And we're making the assumption that 2 is in the same concentration, 0.167, because of them being linked by the value of excess. So we're just going to take B, and we're going to shove it over there and say, does it match? Just one question, does it match, yes or no? It doesn't, not even close. So what does that mean? I thought the value of excess held those two things together. Well, there's two key differences for reaction A at that 30-minute time point right there. They do have the same concentration of 1 and 2. You can measure both those on the IR. You can validate that, it's true. Reaction A has been going for 30 minutes. If there is irreversible catalyst deactivation, a 30-minute reaction could see you sort of leaching catalyst, active catalyst, out of your reaction system. And if you're thinking really critically right now, you could say reaction A at 30 minutes also is at 50% conversion. So it should have 50% of the product present in that reaction flask. What if that's perturbing the rate? Well, that's easy. You just add one reaction to your same excess protocol, and we'll call that B product added. These are the starting molar concentrations for reaction B. We're going to dope in that 50% conversion point there and see if they overlay. They overlay perfectly. That's about as good of an overlay as you could expect to see. With that overlay, you have two very, very important pieces of information that you can extract from that data. One, you for sure have product inhibition because you put in the exact amount of product that you expected to have in those two reactions, and they have the same rate. So the concentration of 1, 2, and product are the same there. So there's product inhibition. We can say there's a negative rate dependence on the concentration of product. But probably more important than that, you can also say you definitely have a robust catalyst. There's no catalyst deactivation. Because everything at this point, at the intersection of the arrows, that's doing the same exact chemistry. It has to be, because the rates are the same. The concentration of all species are the same. That means the concentration of your active catalyst is also the same in reaction A and B. It ran for 30 minutes, it doesn't care. It's as fresh as it was when you hit go on the stopwatch. Okay, so you can go from there and say, I'm going to do my different excess protocol. I told you there were only two things you need to do, same excess and different excess. This looks a lot like what you would do for an initial rates comparison. You just change the concentrations of one of the species and see how the rates compare and say, is it a positive driving force, a negative driving force, or not a driving force? And so with different concentrations of my species 1, until you run out of it, they're doing the same thing. So the same rate at different concentrations, zero order, right? Do the same thing with keeping that concentration consistent, different concentrations of your olefin. Look closely at this. Higher concentrations of the olefin lead to a lower rate. Under these conditions, it takes twice as long for this reaction to get to completion at higher concentration of substrate. So if you have a scenario where you have a lower rate at a higher concentration, that's also a negative rate dependence on that species. Well, so I've labeled all this stuff here. That's not really a typical kinetic scenario. You have no positive driving forces in the stoichiometric components of your reaction. One thing doesn't do anything. Two things hurt you. So you have to go to the catalyst to find a positive driving force in this reaction, and you can do this via initial rates if you really want to, but you can do it with the full reaction progressions and just compare the full reaction progression of one at low concentration to higher concentrations and see that, yes, it gets faster. There's at least a positive rate dependence on the catalyst. So we have approximately a first order rate dependence. You can just call it positive if you want because it's not perfectly first order. But then a zero order, negative order, negative order. So if you tried to smash that back into the catalytic cycle that you had, that's a complete failure. There's no way that that catalytic cycle can account for the kinetics that you're observing in this reaction. So you have to rebuild the catalytic cycle. But the cool thing here is that you're rebuilding a catalytic cycle based on the kinetics. So you can build in your fundamental steps based on what the reaction is telling you, how it's behaving. And so we argued a pre-equilibrium of substrate 1 to the catalyst to give you this now as your active catalyst. So you're effectively saturated in 1. So this is the real key player in the on-cycle catalytic production of your product. The negative rate dependence in the olefin substrate and the olefin, the negative rate dependence in the substrate and the product tell you that you have off-cycle species that are dependent on those concentrations. So you can say, well, if this olefin binds and it pulls the active species off-cycle, you have less of this to go round and round, the rate's going to slow down. But we were able to identify why the ligand was having such a dramatic effect on the rate because it allowed favorable geometric interaction between the hydrogen bond you're going to cleave compared to you have a mixed acetate species that was ligandless, and that geometry is unfavorable. And this is just a rehash of everything I said. I'm kind of picking up now so we can do some questions. But we had very odd kinetic order, zero order, negative order, negative order, only one positive driving force. That's an odd reaction, and the kind of reaction you love to study if you're a kineticist. But we could build from scratch a catalytic cycle to fit that. And so now I'll just sort of leave it to you. If you have the technology to do these in situ measurements, you can do either one. If you're more comfortable with initial rates, that's fine. Nobody's going to tell you not to do it. But if you have data that's this rich, you can get a lot more information in fewer experiments. And I, as a graduate student, had this information and didn't use it. It just went by the wayside. So I would argue heavily for doing this and just push your time axis around until they fit. So these are the people who were involved in the chemistry, a graduate student who took over after I left. And of course, John designed the chemistry. And then these are the guys who worked with me on the palladium chemistry. Dave is an industrial chemist, and Kiri's actually professor now at Scripps. But he was at the time working with Professor Yu. But if you do have questions, I'd be happy to answer anything you want to talk about.